So it is my pleasure to announce Professor Matthias Lesch from the University of Bonn as our next speaker in the Rocky Mountain Mathematical Physics seminar. Professor Lesch got his PhD in 1988 at the University of Marburg and then went to Augsburg, where in 1994 he wrote his habilitation, or finished his habilitation, about a class of singular differential operators and asymptotic methods. He was an assistant professor at Humboldt University in Berlin from 1999 until 2000, then became professor at the University of Arizona in Tucson, and after that moved back to Germany, where he was professor at the University of Cologne from 2001 to 2005, and now is at the University of Bonn since 2005. Matthias Lesch is one of the leading experts in global analysis and spectral geometry, and today he will give us a talk about the spectral flow.
Yeah, thank you very much, Marcus. That was a very flattering introduction. Thank you very much. I feel a little awkward. Okay, so my task was to give a talk on the spectral flow. That was the working title. And okay, so here's this somewhat longer title. It's the title of a paper which I wrote about 2 years ago down under, when traveling was still possible, with Australian people, Chris Bourne, Alan Carey, and Adam Rennie. So it's called the KO-valued spectral flow for skew-adjoint Fredholm operators. Don't be scared. So I will first stick to the task. So I will give a gentle introduction to the spectral flow, and then in the second part of the talk, come to the more specialized aspects of that research paper. It's available on the arXiv and was, meanwhile, it's already online available in Journal of Topology and Analysis. Okay, so so here's the plan. So the talk consists, yeah, basically of 2 major parts. So I will first talk about the classical spectral flow. I refer to it as real and complex. So this is understood in the sense of real numbers and complex numbers. It has to do with K-theory. So you all know that the K-theory over the complex numbers is simpler in a sense than over the real numbers. So I start with the complex case. So I define what the spectral flow is. I will explain to you the Atiyah-Patodi-Singer Robin-Salomon spectral flow theorem, and I will give yeah, 2 at least hint at 2 rigorous ways to define spectral flow. And then there is an intermediate remark which somehow leads to the real case. Then that's I will hint at a recent paper by Schultz, Baldus, and Carey on the mod Zeus mod 2 spectral flow. And then in the second part, I will do real theory. So again, real theory not to be misunderstood as the real thing. Real refers to real numbers. Okay, so what is spectral flow about? So let's say we have a separable Hilbert space denoted by H over the complex numbers, and we have a family of bounded, so B of H, the bounded linear operators on H, so a path of self-adjoint Fredholm operators in this case. Then we can look at the spectrum, and locally the situation looks as follows. So so locally you can choose well, you choose a positive number not in the essential spectrum, which you can do if you have a self-adjoint Fredholm operator, and by sorry, you choose a positive number not in the spectrum, and then in a full neighborhood you will have that this number is not in the spectrum. You can do the same with a negative number. So locally you find a spectral gap here and there, and then finitely many eigenvalues are trapped in between. So okay, so I drew some paths of eigenvalues, how they move along the way, and what you do is you count how many positive ones do I have at the beginning and how many positive ones do I have at the end. And for simplicity, let's assume that at the endpoints 0 is not in the spectrum, which you can do at least by a general position argument. You can do that. So here the net loss of positive eigenvalues is 1. Yeah, so at the beginning you have 3, then you have 2. So the spectral flow from here to there will be -1. Okay. Now this is intuitively very clear. Whether it's rigorous is another question. I will come to that in a second. So so now the spectral flow over the full path will then be the sum of these local spectral flows. Yeah, so the point here is that this picture you have only locally, because here I have at least locally in this over this interval I have a global spectral gap, which I cannot in general I do not have over the full interval from 0 to 1. But at least I can subdivide the interval such that in these subintervals I do have the situation which I depicted before, and then the spectral flow of the full family is the sum of these spectral flows. Okay, so that's you can compute it in this way if you believe that this is a sensible definition. Now, it turns out that this so defined spectral flow is well defined. That's, for instance, explained in a paper by John Phillips in the Canadian Journal of Math in '96. I mean, it goes back to Atiyah-Patodi-Singers to their famous paper on or series of papers on spectral asymmetry, but over there it was explained only at this intuitive level, as I did it before. The spectral flow is path additive, which means, well, it's what it says. If the endpoint of the first part is the initial point of the second path, then the spectral flow of the concatenation is the sum of the spectral flows. Spectral flow is homotopy invariant. This means the following. So I should be a bit more precise about the endpoints. So for the moment, let's assume that at the endpoints, the operator family is invertible. So if I have a homotopy of paths of operators such that the endpoints stay invertible, or more generally that the kernel dimensions at the endpoints stay constant, that's sufficient, then the spectral flow does not change. And third, there is a normalization. Let's say take the one-dimensional Hilbert space and take an operator whose only eigenvalue crosses from -to +. This should have spectral flow 1. That's the normalization. And actually, the properties 2 to 4 characterize spectral flow. So if you have an integer invariant of continuous paths of self-adjoint Fredholm operators with invertible endpoints, say, satisfying 2, 3, 4, then it is automatically the spectroflow. This was certainly a photo theorem, but I proved it in a paper in 2004. It's called the uniqueness of the spectroflow on spaces of unbounded Fredholm operators. Let me show you an application, a mathematical application. It's the Atiyah-Patodi-Singers Robin-Salomon. Okay, so this APS stands for Atiyah-Patodi-Singers RS for Robin-Salomon. The Atiyah-Patodi-Singers Robin-Salomon theorem. So say you have a family of unbounded self-adjoint Fredholm operators called A of X on the real line, indexed by the real line, plus some technical conditions. The technical conditions are awkward to list in all epic details. What you need is that the family has fixed domain, has compact resolvent, plus some differentiability assumptions. These are the Robin-Salomon conditions A1 to 3, which I don't list. This is just technicalities. And then this family has a spectroflow, the spectroflow of A of X. But on the real line, you can form another operator, maybe d by dx plus A of X. And okay, so part of the technical conditions which I should mention is that for large X, say A of X is invertible. Then it turns out that this operator here is a Fredholm operator, and the Fredholm index equals this spectroflow. But that appeared more or less in this paper by Atiyah-Patodi-Singers in the mid-70s, and that was the birth of this stuff in a sense. The proof is intuitively very clear. So we have this characterization. So 2, 3, and 4, path additivity, homotopy invariance, normalization characterize the spectroflow. Well, all we need to show is that left and right hand side satisfy 2, 3, 4. The left hand side is an integer invariant of paths of self-adjoint Fredholm operators. It's tautological that it's homotopy invariant. The Fredholm index is homotopy invariant. Path additivity is, the way I phrased it, a bit awkward, but not too deep as well. So you have to play around a little with boundary value problems and the gluing of indices of Atiyah-Patodi-Singers boundary conditions. Then you show that this index behaves path additively. And well, you have to check normalization. That's the easiest one, but that's easy to present. So let me present that one. So what about the normalization? Well, let's then look at a one-dimensional A of X, which I call f of X. Oh, sorry, which I call f of X. So it's a function which is -1 for small x and +1 for big X, and in between it crosses from -to plus. So the spectroflow should be +1. Now look at the corresponding Atiyah-Patodi-Singers Robin-Salomon operator. So the d by dx plus the multiplication by f. So if you want to compute the Fredholm index of that one, you have to solve an ODE. Well, now if you solve du equals 0, well, you find that u of x is e to the minus x u of 1 for x large, and e to the x u of minus 1 for x small, which is square integrable. So the kernel is one-dimensional. When you do the same for the adjoint, well, you get the opposite condition. So this is certainly not square integrable. So the Fredholm index is 1. Spectroflow is 1, the Fredholm index is 1, so the normalization is fulfilled. That's it. Okay, so that's the Robbins-Salomon's theorem. Now, how to make the definition rigorous? I show you two. The original one by John Phillips, which is very close to the picture I do. Yeah. So so let's start with a family of self-adjoint Fredholm operators T, and you subdivide the interval such that you have spectral gaps in the subintervals, say plus or minus epsilon j. Yeah, so the picture is this. Yeah, so you pick a T, then at least near 0, the spectrum is discrete. So you pick a gap, and by continuity, you can extend locally such that there stays a gap. And since the interval from 0 to 1 is compact, you can cover the interval by finitely many intervals in this way. So so you can achieve this. So you subdivide the intervals such that you have plus or minus epsilon j's, which are not in a spectrum on the full interval from tj minus 1 to tj. And now you formalize this counting, which I mentioned, as follows. You now say the spectral flow is the following. So on each subinterval, you take the rank of the spectral projection onto the interval 0 up to epsilon j applied to the endpoint. So this is nothing but counting the positive eigenvalues at the endpoint. And you subtract the rank of the spectral projection to the interval 0 up to epsilon j of the initial point of this subinterval, which is the number of positive eigenvalues at the beginning. And you can rewrite this. This is nothing but the relative index of the positive spectral projections at the beginning at tj minus 1 and at tj. So so what is the positive spectral projection? Well, you take just the characteristic function of the interval 0 to infinity and apply it to t. Okay, so for orthogonal projections in a Hilbert space, there is also a Fredholm theory. So you call a pair of projections Fredholm if the second applied to the range of the first onto its own range is a Fredholm operator. And the index of that Fredholm operator is called the index of the pair of projections. And it turns out that these two things are just the same. That's simple exercise. And John Phillips showed that well, this definition is independent of the choices made. So if you have another subdivision, you take a common refinement and so on. So it really goes like this, and actually not too long actually to show the properties. So that's one way of doing it. I want to show you a second one, which is more homotopy theoretic, and which then generalizes also to more general situations quite naturally. And that's an approach which I did together with both and John Phillips in the early 2000s. And it uses something which is well known in the spectral theory of unbounded operators, namely the Cayley transform. Yeah, when you have a self-adjoint operator and you take the Cayley transform, you get a unitary operator. Well, not surprising. The Cayley transform wraps the real line once around the circle. So let's introduce some notation. So let's call, say, FSA the space of self-adjoint Fredholm operators, and then the Cayley transform, which maps T to T minus I over T plus I. Well, what does it do? It maps self-adjoint Fredholm operators into unitaries. Yeah, and how do I translate Fredholmness? Fredholmness means 0 is not in the essential spectrum. Well, the Cayley transform maps 0 to -1, obviously. So this means -1 is not in the essential spectrum of that guy. And for later reasons, I can rewrite this condition. So this is the same as saying that U plus 1, not the norm, but the norm in the Corkin algebra, is less than 2. Yeah, so Corkin algebra means I mod out compact operators. So if I take the norm in the algebra of bounded operators modulo compacts, then this condition just means that that I have this norm condition. And well, looks like a complicated space of unitaries, but actually it's not complicated. It so with a little vibration theory, you see that there is a subspace which is homotopy equivalent, namely those unitaries such that U minus identity is trace class. Sorry, yeah, I screwed it up. I should have put a minus here. Yeah, so here we have the condition U minus 1 is small in the Corkin algebra, and this condition means it's even smaller. Yeah, so U minus 1 identity is trace class. Well, and this space, so unitaries of the form 1 plus trace class is nothing but is homotopy equivalent to the infinite unitary group. So now let's take a path here in this space, and let's for simplicity take a closed path. So if I have a closed path of self-adjoint Fredholm operators, I take the Cayley transform and map it to this space. Well, and here I have a homotopy equivalence, so I have actually a path of unitaries of the form 1 plus trace class, or infinite unitaries. So they have here I have the binding number. So and this is just a spectral flow. Yeah. So the spectral flow, in a sense, after taking the Cayley transform, is nothing but the good old winding number. So you all know what the winding number is. So if I have a path of, let's say, I have a path in the complex plane which avoids 0, well, I take this integral, the f over f, and I get an integer. And if I have a path of unitaries of the form 1 plus trace class, I can take, instead of this, I can take trace f inverse df. And that gives me an integer called the winding number. Okay, so here I have explained how to relate the spectral flow for closed paths to the winding number. It's not too hard to go from here to arbitrary paths with invertible endpoints. And I have prepared another slide for that, but let me push this maybe to the discussion session if you're interested. So that was the integer valued spectral flow. Now, quite recently, people also from the physics community, so Schulz-Baldus is half physicist, half mathematician, came up with a mod Z version of spectral flow. And a priori, the link was not so clear, and so one of my plans is to show what the link is. So what did they do? Well, let's now say we have a separable Hilbert space over the real numbers. And okay, so now you have a path of Fredholm operators. Yeah, instead of self-adjoint, take skew-adjoint. Yeah, I'm a bit hard-pressed to motivate this. Let me put it like this. I should have talked about skew-adjoint families from the very beginning, but in the complex case, it doesn't matter. There is I. So if I have a path of if I have a skew-adjoint Fredholm operator multiplied by I have a self-adjoint one, and vice versa. In a real Hilbert space, that's not possible. So it's a difference. So I take a path of skew-adjoint Fredholm operators. Well, in that case, eigenvalues come in obviously in pairs. Yeah, so you have this kind of mirror picture. So whenever I have an eigenvalue, its negative one is also an eigenvalue. So if I have an eigenvalue crossing from plus to minus, I have one which crosses from minus to plus. So the naive spectral flow certainly is 0, but there is so what these authors showed is that there is an assignment of which extracts from such paths a number mod 2z, which otherwise has the same formal properties. So path additive, homotopy invariant, and it's non-trivial. So there is a normalization. There is one example of a non-zero spectral flow. So what is also interesting, it's not as simple to explain this by picture, because it's the mod 2 spectral flow cannot be explained by looking just at the graph of eigenvalues. Yeah, so as I said, crossings come in pairs, and it's not so clear whether crossing is non-trivial or not. So I will not go too much into details how they did that. So roughly they do the following. Roughly they show that locally, so you do a similar covering of the subdivision of the interval, which I did before, and then locally there is an orthogonal operator which conjugates the endpoints to each other. And now the real orthogonal group has two connected components. So then the mod 2 spectral flow from one endpoint to the next one is the sign of the determinant of this operator here. Of course, I'm cheating because all this takes place in an infinite dimensional Hilbert space. It's not so clear what this determinant should be, but so there are many details to be filled in. Now, when I saw this, well, I asked myself, well, so spectral flow is related to the homotopy theory of the space of Fredholm operators. The spaces of homotopy theory of the space of Fredholm operators is related to K theory. So so in real K theory, you get mod 2 indices. So there should be a unified approach to spectral flow, which has these two phenomena, which I showed here as examples. So the goal, therefore, is the following. So I want to give a coherent, unified approach to spectral flow using Clifford index theory. And also one should then, of course, recover another mod 2 case. So there are two Z mod 2 groups in the real K theory of the real numbers. And also there should be an analog of the Robin-Salomon theorem in KO then. So, and as I said, the key to this should be the homotopy theory of the spaces of Fredholm operators, or the homotopy theory of the classifying spaces of K theory after Atiyah and Singer. So this is Atiyah and Singer. That's a paper in '69. It's called Index Theory of Skew-adjoint Fredholm operators in the IHS Publication Mathématique, 1969. And in order to explain this, I will first recast the complex case in that language, and then switch to the real case. So here's the second part of my talk. Then the real theory. So and as I said, let me first look at the complex case again, but from the point of view of homotopy theory. So we take a complex Hilbert space. Okay. So we take a complex Hilbert space, and I denote by script F those bounded operators on H such that T is Fredholm. And there is the classical Atiyani theorem, namely that that script F is a classifying space for K0. That's very intuitive to explain. So if you have a family of operators in F parameterized over the space X, then after some stabilization, the kernel and the co-kernel of that family will be a vector bundle over the space, and then the difference will be an element of K0 of the space. Yeah, and that construction actually shows that F is a classifying space for K0. Well, now let's go to the path space. Then the path space of F is a classifying space for K-1. now the nice thing is that this sparse path space here can be replaced by another space of Fredholm operators. So it can be made much more concretely instead of just taking here the path space. Namely, we denote by f hat the self-adjoint Fredholm operators. And now this space turns out to have 3 connected components, 2 trivial ones and 1 interesting one. So if you have a self-adjoint Fredholm operator, there are 3 possibilities. It can be essentially positive, it can be essentially negative, or it can be neither one. So the essentially positive ones are contractible. The essentially negative ones are contractible as well. But the space F star hat, that's the interesting space. And here is Atiyah-Patodi-Singers theorem from '69, namely this space F hat star, so the self-adjoint Fredholm operators which are neither essentially positive nor essentially negative, this is homotopy equivalent to the path space of F. And the homotopy equivalence is very concrete. So here it is. Yeah, so actually it's the path space of paths from +1 to -1 to be precise. So if you have a t here, the path is cosine pi t identity plus sine pi t times t, and the little t runs from 0 to 1. Yeah, but since this classifies k minus k1, the self-adjoint Fredholm operators classify k1. And now we have another look at the spectral flow. Okay, so yeah, there is this remark that we cannot hope to obtain a single invariant, an invariant for a single self-adjoint Fredholm operator, of course, because k1 of the point is 0, but we get an invariant for paths. So if you have a closed path of self-adjoint Fredholm operators, so if you look at pi 1 of this f hat star space with base point, well, since it's a classifying space for k1, this is k1 of the suspension of the complex numbers, which is k2 of c. And I would like to call this map here SF2. So that this is a very natural map which is obtained just by these homotopy equivalences. And from k2 of c, you have the Bott map into the integers. Well, and that's and this here, that's the spectral flow. Okay, so that's the explanation of spectral flow in terms of classifying spaces for the K-functor. So this theorem is nothing more than just an observation. So if you follow the definitions, then you see that the Bott map composed with this SF2 is just the ordinary spectral flow. So, but from this, it is now clear that there should something similar in the real K theory. So here's the table of K groups. Yeah, so the complex K theory is simple. Yeah, so it's Z0, Z0, and so on, 2 periodic. And well, there is only one integer invariant if you want. It's either just the Fredholm index of a Fredholm operator, or if you twist it around often enough, it's a spectral flow of a closed path of self-adjoint Fredholm operators. But over the real numbers, there is a bit more. So there are Z mod 2Zs here. Yeah. And it turns out that this Z mod 2Z, that's the mod 2 index of Carey, Phillips, and Schulz-Baldus, which I mentioned. Yeah, and there should be another one. And yeah, actually, that also exists in the literature. It's discovered in another paper, completely independent of this theory here by Doll, Schulz-Baldus, and Butterstart. They call it the parity flow. And now my final goal is now just to give an approach to spectral flow which covers all of them at once, so to speak. And for doing that, one has to go a bit deeper into the Atiyah-Patodi-Shapiro theory for the Clifford modules and real K theory. So let me briefly introduce some notation for that. So I denote by CLRS the real Clifford algebra with R self-adjoint generators of square 1 and S skew-adjoint generators of square -1. Let me emphasize that the notation, unfortunately, is not uniform in the literature. So my convention of the letters R and S is the one of Atiyah-Patodi-Shapiro and of Kasparov. It is opposite to the one in the well-known book by Lawson-Michelson. So if you compare the Lawson-Michelson, you have to switch, you have to flip the two letters. So this means that, yeah, so the E's and the F's, they all anti-commute, and the E's have square 1 and the F's have square -1. And with this, you can do some nice things, namely, wait a second. I denote by MRS the equivalence classes of finite dimensional CLRS modules. And by MRS hat, the equivalence classes of graded finite dimensional CLRS modules. And now if you have a CLRS module, you can be lucky. It can be that it even admits a CLRS +1 structure if you just find another Clifford generator in the module which acts on the module. So and then you take the quotient. So I say ARS is the quotient. Yeah, in the graded situation, it's just MRS hat modulo MRS +1 hat. Or in the ungraded case, you have to shift the second index by 1. And the famous observation of Atiyah-Patodi-Shapiro is that ARS is nothing but KO of the real numbers, where the index is S is the difference. Yeah, so ARS is KO of S minus R of the reals. So this means this group ARS is 8-periodic, and it's given as this. So A00 is Z, then Z mod 2Z, Z mod 2Z, and so on. The isomorphism can even be explained in a little. I should maybe do all of them, but maybe one example. Yeah, so there is a direct explicit map from ARS into the corresponding groups. Okay, in the case R equals S equals 0, it's very easy to explain. So this case can only be covered in the graded situation. So M00 hat is just graded vector spaces. And M01 hat is graded vector space with one skew-adjoint symmetry. Well, if a vector space has a skew-adjoint symmetry, which needs to be odd, this I did not say. So the Clifford generators then act as an odd element. So this means that the positive and negatively graded subspace have to have the same dimension. So this means that if you have a graded vector space, you just take the difference of the dimension of the positive and negative graded subspace, and that gives the an isomorphism of A00 onto the integers. Well, and by looking at the Clifford generators, you can play this game for all other RS as well. And now there are analogs of the spaces of self-adjoint Fredholm operators in this Clifford setting. You now denote by FRS plus 1 the skew-adjoint Fredholm operators, which are CLRS antilinear. So assume you have a real Hilbert space and you have the Clifford algebra CLRS acting on this space by unitary, with the Clifford generators being unitary operators, either square 1 or square minus 1. And yeah, FRS plus 1 are those skew-adjoint Fredholm operators which are CLRS antilinear. And Atiyah and Singer showed in this quoted paper from 1969 that this space is a classifying space for KOR minus S1. Similarly to the fact that the non-trivial component of the self-adjoint Fredholm operators is a classifying space for K1. And actually, the Fredholm index on this space can easily be or nicely be described. And here it is. So if I have a Fredholm operator, skew-adjoint Clifford RS antilinear, well, I look at its kernel. On the kernel, I have the Clifford algebra CLRS acting. And I view it as ungraded. So this gives me a class in ARS plus 1, which is KOS plus 1 minus R. Something's wrong with this index here, huh? Something's wrong with the indices. Okay, give me a break. I'm unhappy about the 2 here, but the basic construction is the correct one. Yeah, so you take the kernel, the operator has a certain Clifford symmetry, you view this as a module with Clifford symmetry, and you take its class. That's the Fredholm index. And now by going to path spaces, we also recover the spectral flow then in this business. So, and you produce a KO version of spectral flow, which is completely in line with this complex homotopy theoretic spectral flow, which I gave you before. It's only notationally a bit more involved. Let me, maybe briefly go over it. I'm a bit unsure about the timing because we started a bit after, but 5 more minutes I should have.
Yeah, you have actually even 10. That's okay.
Okay, good. I try to do my best. Yeah, it should work out. So yeah, so you have to play a bit with these operators which make up Clifford generators. So you take a real Hilbert space and you assume that you have a CLRS plus 1 action on it. So this means you have sufficiently many unitaries satisfying the Clifford relations, and you also have to make sure that none of the plus I eigenspaces is finite, so that all irreps of the Clifford algebra have infinite multiplicity. So this takes place in a separable Hilbert space, and the irreps of the Clifford algebra occur often enough. So this means you have E1 up to ER and F1 up to Fs plus 1 unitaries of square 1 of square minus 1 anti-commuting. And now you so in order to so the pattern in this Atiyah-Patodi-Shapiro description is you have a module with Clifford symmetry and you look for an additional Clifford symmetry. So if there exists one, the module is trivial in the group, otherwise it's not. So we look at all possible additional Clifford symmetries. So I denote by JRS plus 1 those unitaries, skew-adjoint, square minus 1, which anti-commute with CLRS. And then you get the analogs of these omega spaces, which we saw at the very beginning. So so omega res bar is those T's such that T minus Fs is compact. So Fs is the one of the last generators here, and the twiddled space is a bit bigger. So that's this condition that you have. So the difference in the norm in the Calkin algebra is less than 2. And then, as in the complex case, one can show that the Cayley transform gives a homotopy equivalence from the Fredholm operators of type Rs plus 1 into this omega twiddle of type Rs. So that's completely the completely analogous statement to the one we had over the complex numbers at the beginning. And then consequently, you get the same diagram. So so if you have a closed path of Fredholm operators in here, well, via the Cayley transform, you get a loop in this omega twiddle space. Well, and this homotopy group is a KO group. So this turns out to be KO Rs plus 1 of R, and this is then, so to speak, the KO version of the spectral flow, which contains all spectral flows we have seen before as special cases. That's the result, so to speak. So this SFRS plus 2, which exists for all R and S, of course, depending only on the difference of R and S mod 8. Obviously, so there are only 8 cases, and this is characterized by path additivity, homotopy invariance, and normalization. Normalization is not so simple to explain. Now, in this Clifford module case, you have to go into the Atiyah-Patodi-Singers reconstruction. So, yeah, so as I haven't stated this as a formal theorem, but again, so SF02 is the integer spectral flow, and SF12 and SF22 are the mod 2 spectral flows of Carey, Schultz-Baldes, and of Doll-Waterstroud we have seen before. You know, may I ask you, so let me skip that one. You may ask yourself whether there is a Robin-Salomon theorem. There is one. Before doing that, let me also mention that, well, there is also a formula a la John Phillips in the complex case. So let me go back to that to make sure that you know what I mean. Let me go back. No. Yeah, it was this one. Yeah, so you have a path, you subdivide the interval, and then such that you have a spectral gap condition, and then the spectral flow is the sum over the subintervals of relative indices, in this case, the positive spectral projections. And now this has a complete analog in general. And here it is. Yeah, so if I have a family of skew-adjoint Fredholm operators of type RS+1, so Clifford RS symmetry, well, you assume at invertibility at the endpoints, and then you take the path of the phases. Yeah, there are some technical issues. Yeah, so of course on the way the T does not need to be invertible, but essentially that's what you're doing, and these phases are skew-adjoint operators with a certain Clifford symmetry. And it turns out that for such object, there is also a relative index, which is the Clifford analog of the relative index of a pair of projections. And then it turns out that that the spectral flow of the path is the sum of these relative indices of these phases. Yeah, so this all works out quite nicely. And finally, there is also a KO analog of the Robin-Salomon theorem. So if you have a family of unbounded skew-adjoint Fredholm operators with Clifford symmetry of type R and S, otherwise the same technical conditions as in the Robin-Salomon theorem, you can form a Fredholm operator whose Clifford Fredholm index is the Clifford spectral flow of that family. You cannot take d by dx plus a of x. You have to take care of the Clifford symmetries. You have to blow up the matrix. This has a clear motivation. Here I will explain in a second. So if you form this matrix comprises of d by dx and a of x minus a of x. And this is a Fredholm operator with a bit more Clifford symmetry. That's due to the fact that this matrix has certain symmetries. So actually, here's are the Clifford generators explicitly. So if E and F are the Clifford generators, you blow them up just by direct sum. And there is an additional symmetry, which is just this off-diagonal matrix. So, and this D is therefore a Fredholm operator of Clifford symmetry RNS plus 1. Hence, it has a Fredholm index of type RS plus 2, which is the spectral flow of that family. So it really fits perfectly. Despite that this is very nice, I don't have an application of that. I have to admit, honestly. Now, where does this matrix come from? That's not a surprise whatsoever. So here's the heuristic. So the guiding principle is the Kasparov product. So if you have a family of Fredholm operators of the given Clifford symmetry, actually it is a class in KKRS plus 1. And the fundamental class d by dx is in KK1 of the order of functions vanishing at infinity and R. And the Kasparov product of these two is just this matrix. So when you look up, it's explained as an example even in Blackadder's book, I think. So that explains why one has to take this matrix and why it is quite natural. And the proof works along the same line as in the complex case. It's by the characterizations through path additivity, homotopy, invariance, and normalization. I haven't said anything about the normalizations in the Clifford case. You have to really go through this Atiyah-Patodi-Singers reconstruction case by case and have to check. It's a bit more awkward, but otherwise very, very clear. Yeah, I think that's what I wanted to say up to now, and thank you for your patience.
Yeah, let's thank the speaker for the very nice talk. Are there questions? So don't.
So Marcus, can I ask a question?
Sure. Yeah.
Sure.
Hi, Sean.
Hi. So hi, Matthias.
Hi.
Thank you for the nice talk. So can I ask you a question or maybe a general reference? So have you seen works about generalizing this kind of a spectral flow to the case with a group action?
With a group action.
So I mean
okay.
operators, self-adjoint operators or Fredholm operators invariant under group action.
Yeah, so I guess you know the work of Charlotte Wahl. Charlotte Wahl? It doesn't quite answer the question. I mean, she worked on spectral flow with respect to an auxiliary C-star algebra. Yeah, so you have a so roughly speaking, you have a path of Fredholm operators over C-star algebra. And then you get as spectral flow, you get an index in the K theory of the underlying C-star algebra. I think that with group actions, this should somehow fit under this roof. Yeah, if you take, say, as a basic object the group C star algebra. But strictly speaking, no, I don't know of any paper where it is really addressed as such with group actions. No, I don't know.
Yeah, thank you. I have another question. So,
Yep, please.
yeah, so here we consider a path and introduce the flows, right? So is it kind of reasonable or possible to consider instead of a path, maybe a triangle, or maybe a kind of a simplex, and then a family of self-adjoint or Fredholm operators, and then define some kind of higher version of the flow or the
Should certainly work. Yes. Wait a second. I mean, this picture here, of course, there is no reason to confine yourself to pi1. I mean, you can replace pi1 by pi anything, and instead you then have maps from simplices or spheres into Fredholm operators. So this basic diagram, I don't see any problems. There is one aspect which cannot be recovered in the higher version. So people like to have these indices also for non-closed paths. So if you have a path of operators which is with, say, invertible endpoints, say, then you can still do something. It's very simple. You close up the path in a contractible neighborhood of the base point. This cannot be mimicked in higher. Well, I don't see how this could be mimicked in the higher case.
Okay, further questions?
Maybe just a comment. I think that Heng Wang did something with equivariant spectral flow at some point. I don't know if you want to look it up or something like that. I just sort of remember a talk from a while ago, but you know, Heng Wang.
She's in
Like
Shanghai.
this?
Yeah, exactly. She's in Shanghai.
Okay, thank you.
Further question? Daniel, I want to maybe briefly come up with what we have been discussed. Do you want to, about the spectral flow in the quantum matter theory? So we have been thinking about the relation to this spectral flow you talked about, Matthias. And anyway, Daniel, do you have some?
Well, I think it would, can you tell us about any of the physics applications of this? In particular, I think you mentioned the Z2 spectral flow has physics applications.
Yeah, okay, so I can only explain it in layman's terms. Yeah, so I'm really a physics layman. But I mean, what do the topological insulator guys do? Well, the physical system is given by a bunch of symmetries. Yeah, so and all these symmetries are Clifford generators in a sense. And you well, you ask yourself how how many possible theories do I have? And at least there is a crude classification up to homotopy equivalence of the possible systems. Yeah, so and that's these numerical indices somehow classify these systems up to homotopy equivalence. That's how I understand what the topological insulated guys do with this in a certain sense. Yeah. I cannot really comment on how sensible this is.
Thank you, though. That's
helpful.
Mean,
it's very clear that what you just explained today is of high relevance to this whole topological theory of quantum matter. Yeah, like these topological insulators, for example. And there's the particular one particular point is that some authors, namely Nachtigall, Bachmann, and others, used the term spectral flow as well. But it seems it's not exactly, the interesting thing is it's not exactly the same like what you defined, and so meaning the traditional global analysis definition, but it's a certain path in an automorphism group of the C-star algebra with certain spectral properties in a representation. And despite the same name and in principle the same name for different things, there are striking similarities. And this is a bit the question we had in our group, Daniel, Agnes, Mike Emily, and so on, in how far this is related to phenomena which come up in the, let's call it, global analysis notion of spectral flow.
Okay, can you give me a reference for that?
Yes, I can just, you know what, I have this article, Nachtigall, Sims, and Young on quasi-locality bounds for quantum lattice systems, part 1. And yeah, actually there's spectral flow, and then a subtitle, Lieb-Robinson bounds, quasi-local maps, and spectral flow automorphisms. Yeah, I can, I can send you, let me just send you. Can send you the archive number, and later on I will.
Okay, that would be great, actually.
Yeah. So here, this is. So here's the archive number. It is published, but I would have to look it up. Where I think it's communications math physics, if I remember correctly. In any case, it's very interesting, the connection.
Okay, thank you. I certainly have a look at this. Why, my goodness, it's 106 pages.
Yeah.
Good.
Okay. Yeah.
So I know what to do tonight.
Yeah. Okay. Are there further questions? No, then let's thank the speaker again. And in 2 weeks, we will with the talk
thank you very much for hosting me. It was quite fun and nice deviation from the daily routine, which I have here. Starts to get a bit boring.
Good. Okay.
Good. Okay. Good.
Goodbye, everybody.
Then take care and goodbye.